Right, so the next speaker is Julia Ericson, and you're a PhD student at the Karolinska Institutet in the group of Torkel Klingberg. And we will be talking about measuring functional connectivity and then addressing it to working memory. Please.
Yes. Hi. So first of all, I just want to say thank you so much for inviting me. As you said, I'm doing my PhD in cognitive neuroscience at KI, where I focus on spatial working memory and attention. But actually, I have a background here from KTH, actually, where I did both my bachelor's and my master's in data-driven statistics and machine learning. So a lot of the things that I do now is to apply data-driven methods to study like large-scale cortical networks that emerge under states of high working memory load and attention. And I will talk a bit more about these working memory networks towards the end of the talk. But the beginning is mainly going to be focused on the imaging technique MEG that we use and how MEG activity can be used to estimate these large-scale cortical networks and how we using them functional connectivity. So before we start, I just want to take a moment to just acknowledge the other people in my group. So we have my supervisor, Torkel, and then Nieves is here as well, who's doing a lot of the data analysis with me. Jeannie has been collecting like all the data with me, so that's been very helpful. And we do it in the NetMeg facilities here in, at KI, which is the only facility we have here in Sweden that do whole head MEG. And they're also extremely helpful when it comes to setting up experiments. And then finally, the Palva lab in Finland, who we are collaborating with in our studies. And they are really good at the methodological stuff. So a lot of the method stuff that I'm going to go through has been developed in your lab. Okay, so an overview then, what I'm going to go through. We'll start by going through what MEG is and what functional connectivity is, why we're interested in it. Then we're going to go through some methodological challenges when it comes to analyzing this. And then finally, I'll give an example from my own research on working memory. Okay, so then to start, just what is MEG? It's even if you don't know what MEG is, you probably know what EEG is. So then you get this very fancy cap that I have on here. And you put electrodes and then you measure the electric current or the electric field generated by the neurons. We get really good temporal resolution from EEG. A problem though is spatial resolution. And a big problem here is electric conductivity. So if you imagine here that this is the cross section of the head, where your nose and the ears, and then you have this electric field generated by the red source. Now, every time you pass from one medium to the next with a different electric conductivity, you're going to get the field spread or diffraction, just as happens in light. So that means that's difficult to estimate the origin of the source. Now, the magnetic activity doesn't have this problem. So the magnetic activity also generated by the neurons. So what we can do instead to gain a spatial resolution is that we can use MEG instead. MEG is a bit more, or it's a lot more complicated machinery compared to EEG. So like the magnetic field that's generated, it's like 1,000 times less than the Earth's magnetic field. So you need to be in this magnetically shielded room, and then you also have superconducting sensors. So you need to have like helium in this, liquid helium in this thing above to cool it down. So it is more complicated and it's more expensive, but what you do gain from it compared to EEG is a spatial resolution. Now, of course, you can't measure the activity coming from single neurons, but through the synaptic interactions. The firing of neurons can become synchronized, which results in more large-scale changes in the local field potential, which we can measure. A lot of the time, an oscillatory pattern can be seen in the local field potential, and this seems to arise from local inhibitory connections, feedback connections. And these oscillations, these are like the standard which people have already been talking about. We group them into different frequency bands. So we have delta, theta, alpha, beta, and gamma, which is the highest, so like everything above 30 hertz. And depending on like which state you're in, you can get different peaks in the power spectrum. So the normal one is just the like typical example is when you close your eyes and you get an increased alpha activity coming from the back of the brain. But you see different types of oscillatory patterns here, depending on a lot of different, like if you're sleeping or if it's like a psychedelic state, and so on. Everything from beta and downwards, we call it macroscopic oscillations. And these are a lot of the things that where you would see peaks in MEG activity. However, cortical local populations, they only seem to be oscillating at the gamma frequency, some 30 hertz and above. So how then are these macroscopic oscillations created? Well, it seems that they can be created through the synchronization then of these local populations. So for example, in computational models, we've seen, that was a little bit what you talked about this morning, that when you have a time delay between oscillatory nodes, they can start to oscillate at a lower frequency. But it doesn't need to be cortical connections. We can also have connections to deeper structures in the brain, like the thalamocortical loop, for example. And it seems like the longer the time delay between these populations, the lower the frequency of the synchronized network. So when you record MEG activity, you also see that the sources are, you see a correlation between the sources. And we call this functional connectivity. Also because, of course, it doesn't have to be necessarily a structural connectivity between them. It can be, but they can also be connected indirectly. We measure functional connectivity using the phase locking value. There are multiple ways of measuring it. We use the phase locking value. And the phase locking value is basically just a measure of how consistent the phase lag is between two sources. So for basically each point in time here, you calculate the phase lag and you describe it as this vector on the imaginary plane, where the angle there is going to be the phase lag at that specific time point. And in a case, for example, where the two, like in this case, where they're completely synchronized, the vector there at each point in time is going to point in the same direction. So you're going to get a vector of length n pointing in that direction. And then when you divide by n, you get 1 back. So 1 is the highest PLV that we can have. Then, of course, if it's completely unsynchronized, it will go in all like different direction. It's going to go towards 0. Yeah, so that was just a bit of background what MEG is and what functional connectivity is, why we're interested in this functional connectivity. Yeah, and just interrupt me if you have any questions at some point. But now I'll go through then some problems that we face when calculating functional connectivity. And the one major problem that we have is source mixing. So source mixing is when we wrongly estimate activity from a single source as originating from multiple sources. And this happens due to this signal leakage in the source reconstruction. So you have your source that's generating a magnetic field that's picked up by multiple sensors around. So Each sensor will be a linear combination of a lot of different sources. And these beta values here we can estimate because they depend on the distance from the sensor to the source and also the direction of the magnetic field at the source. And then we can reconstruct then the source activity from this. The problem here is that our sensor space, has a rank of about 70, and there's a lot more sources in the brain that we want to estimate. And this means that in the source reconstruction, then we get this leakage when activity from one source is actually projected onto multiple neighboring sources. And this, of course, will create an artificial synchronization because it's the same source, same activity in two different sources. This is some the simulations of what happens under different levels of source mixing. So here to the left, the X value here, that's the true synchronization. The M values are different levels of source mixing. And then of course, even if you have zero true synchronization with source mixing, you're gonna get a positive PLV value, or larger than zero. You think this is only a problem because these have a zero phase lag between them because it's the same signal really. However, it's not only a problem when the phase lag is zero. What you see here to the right is the phase difference and how the PLV is affected by source mixing at different phase lags. And as you can see, it's not only a problem at zero because you get an interference between the actual signal and the true signal, which means that if you have source mixing, you're going to bias your results towards low frequencies and cancel out, or no, sorry, not low frequencies, low phase lags, and cancel out activity from larger phase lags. So that's what's shown here. Here's with zero source mixing, this green distribution there, where there's the maximum around 90, between 45, 90 degrees. But then with source mixing, the whole distribution gets pushed towards a lower phase lag because of this interference. A very easy and really, yes.
How do you know when you have source mixing? Because it certainly makes sense, but how can you tell from the results that there was source mixing?
So this is a simulation.
Okay, so in reality, it's
in the reality, you don't know. That's the So this is just a simulation of what happens. A really crude way to deal with this is to just take the imaginary part of the phase locking value. So the imaginary part is not going to be affected by the source mixing. So here you can sort of see the difference, especially to the right there, of just the PLV or the imaginary part of the PLV. Of course, this removes all your connectivity at the phase lag of 0 and the phase lag of 180. However, what it does, and what's the nice thing about this, is that the more source mixing you have, the lower will your imaginary PLV be, which is nice because it means that you can't create patterns in your data by having poorly reconstructed data, right? Because that's a problem otherwise. And a lot of the time, what we do anyways is that we compare the synchronization under different conditions. So it's normally a difference in phase lag a difference in synchronization that we're looking at, sorry. And there's no change in phase lag. So that's the reason for using IPLV instead. There are, of course, still problems with this, and it's something that we call ghost interactions, and they happen when you have a true synchronization. So here to the left, that's the case where you have no true synchronization. So you have this blue node here, and you have this red node here. And because of source mixing, there's an artificial synchronization to the neighboring sources, both for the blue one and the red one. And when we take the IPLV, those are going to be removed because they have no imaginary component. To the right, though, if we have a true synchronization, so the blue source is synchronized with the red one. We have this true connection there between them, but because the signal is spread out over multiple sources, there's going to be a lot of connections from an area around the blue source and an area around the red source. And those are going to have an imaginary component, right? Because the phase lag is not only going to be 0 there. So those you don't remove, like they can't be removed. That's what you see there furthest to the right. Of course, these correlations, these connections are correlated, so you can sort of group this into just one edge. But what happens there is that you reduce your spatial resolution a bit because you don't actually know where the center is. So these problems with source mixing, you can deal with them, and there are ways to make them better, but you're never actually going to completely remove the problem. And this has an impact on our spatial resolution. So in general, this means that MEG is not really the method that you would use if you're doing like a region of interest study where you're focused on specific locations. But it's really good if you're interested in large-scale dynamics, where the exact position of the source is not the main interest. So with that said, I'll go through and give an example from my research on working memory. And what we're interested in is to look at synchronization during working memory maintenance. So just quickly, working memory, you probably all know, but just go through anyways. It's the ability to maintain information in memory under shorter periods of time. So yeah, for example, I'm borrowing my friend's phone. I need to put in, I ask them what the PIN code is, and they say, oh, 3285. And then once I type that in, as I'm typing it in, I still have to keep that information in mind. And then I can completely forget it. So that's working memory. Now, what we're mostly interested in here is spatial working memory. So remembering positions in space. And as I said before in the beginning, I touched on attention as well. This is, of course, very related to attention, spatial attention, because remembering a position in space and focusing on position in space, that's two like similar things. And there is a lot of overlap here in the neural activity. There's also as you might know from your own brains, to like our working memory is quite limited. It's limited to just a few items, like 5, 6, or so. Yeah, either the items or what we call the working memory load. And what we wanted to do then was we wanted to investigate if any cortical networks emerge under working memory maintenance of higher loads. So for that, we used the following task. So you have this 4x4 grid, and then dots on the grid light up, and you remember the order, and this you do in the scanner. And basically what we do is that we extract these periods in between the cues. And then we get the representation of what the memory is like for load 0, load 1, load 2, load 3, load 4, or 5. yeah, this is just what the test looks like. And then you fill in, and it's very, very straightforward. Let me see if I can. Yeah. And as I said, from this, we wanted to define sort of like a working memory network. And for an edge in the brain to be part of this working memory network, we said that there had to be a significant change in synchronization as a function of load. Those sort of the criteria to be part of it. A problem when looking at more of these complex like cognitive functions is that the pattern of activity can vary a lot from person to person. So what we now I have something on my screen.
Let's zoom.
Yeah, I'm not connected to Zoom.
No.
Okay, so yeah, as I was saying, there's a lot of intermediate vulnerability here. So to deal with this, what we did was that instead of having like a large group of people and then taking the average, we just had a few subjects and then we scanned them multiple times. And then we sort of treated each subject then as sort of like its own replication unit. So we did the whole analysis from just within single subjects. And then we sort of, okay, looked at what's, are there any similarities between these subjects? So the first thing to do was just to look globally, like where do we have a change in, synchronization? So this is what we see. These are for two subjects. Here's 3 measurements from the first, here's 3 measurements from the second subject. As you can see, there is this increase in the alpha band that's really clear in all subjects, both subjects. What's interesting though, it might not be super clear from here, but the maximum frequency here is about 2 hertz higher than for this subject. So that, and this was stable the whole time, like over all the measurement sessions. So it seemed like they had different peak frequencies. But there was a clear increase in alpha synchronization here during the maintenance periods. Here is another subject. As you see in this one, there's the tendency, or in the beginning, there's the emergence of alpha synchronization as well for the loads 2, 3, 4 here in the middle, but then it goes back again for higher loads. So there's a change of alpha synchronization in the subject as well, but it's not as clear of an increase throughout the whole trial. It goes up and then it goes down again. Just a quick word as well of synchronization versus power, because we look at power as well. Usually what we see is that, I mean, all the time when we have like a synchronization, we of course also have an increase of power. So that's something like that gets confused when I talk about synchronization. Like I don't only mean that there's a synchronization increase, of course there's also a power increase because these two things are very related. However, what I find is that I normally get a lot better like signal to noise ratio when I look at synchronization. And then also, of course, it's normalized to begin with, which makes it quite nice. It's always, yeah, values between 0 and 1. Yeah, so that was just a quick side note that, of course, there will be power changes as well. Yeah. Then what we did was to identify where this synchronization change happened. And these are, just a heads up, these have different scales on the heat maps there. So this is more just to look at where it's happening and the different people. So you can see it looks, there are similarities, overlaps between the participants, but there are also quite large individual differences. But then within a single subject or multiple sessions, it's quite similar. So for this one, you have, I mean, there's of course going to be a few differences, but you have this activity up here and consistently these occipital regions as well. But yeah, also, as you can see, these are quite large scale networks with activity in alpha activity going on in a lot of different areas. So to summarize this first part, alpha synchronization changes during working memory maintenance as a function of load. The networks that we identify, they are large and they scan like both the parietal, occipital, and temporal, and somatomotor areas, a lot of somatomotor areas as well. And the networks differ between the subjects, but they're quite stable across time. Now there's one question that I haven't answered at all here, and that is, okay, well, is alpha synchronization, how is it related to working memory capacity? Like, is it good for working memory capacity? Does having a high alpha synchronization actually mean that you perform better, or was it better for the person who could actually then reduce their synchronization? Here, if we had a lot of subjects, we could just sort of correlate that, see how well they performed and how high the alpha synchronization is. However, of course, we have 4 subjects, so you can't really do that. So what we did instead was that we had them train on this task I showed you before. They were training on that task at home every day. So this was over a period of 2 months that we scanned them. And this meant that they increased their performance on this task. Then, of course, we don't only want to scan this task because there might be something that's just task related. So we also scan them on this other transfer task, which is also a working memory task, but which they were not practicing every day. And then we had this control task, which was just a verbal recognition task. So they had to just listen to see if they heard the letter Q. So very boring task. And what we did here was that we found this increase here of alpha synchronization that increased linearly throughout the training periods in the train tasks. So at this moment, we're only analyzing the train task. It was only 3 subjects. Interestingly, the subject I showed you before, where there was like an increase and then a decrease, that person did not show any change there. So we don't really know. Why, but it was present in the other 3. We just did a quick, I tried not to do any sort of group analysis, but I was a bit curious to see where the overlaps were. And the overlaps between these subjects is here in the parietal areas and around the frontal eye field there. And that's sort of the areas that you would get if you were doing like an fMRI study on working memory and seeing where the activity is. You get a lot of, especially parietal and frontal eye field activations. So that was just sort of nice to, a good check to see. Now we took these networks and then we looked at what happened in the control task and in the transfer task. And what we would assume was that, okay, well, if this has to do with working memory capacity, then we should also see the same increase in the transfer task, but not in the control task. So that is what we saw as well. An increase over time for the transfer but not in the control task. And then just a final thing as well. All this that I've been doing is that I can do with the PLV is looking at undirected synchronization. However, what we're trying to look a bit more at the moment is also directed synchronization. What we use here is something called delayed transfer entropy. And here you basically look at conditional probabilities using the KL divergence. So if basically it's based on the fact that if signal A causes signal B at the time delay delta there, then the conditional probability of the future B, be it delta, conditioned on its own past, should be different than be it delta conditioned on its own past and of A's past. So A is helping to predict the future of B. The state X here that we're looking at, that's the phase of the alpha oscillation. So we just like numerically estimate the probability distribution here. And we do this within the single subjects. And it works because we have quite a lot of, like million time points then from each participant over all these sessions. And we compare the delayed transfer entropy under low alpha synchronization versus high alpha synchronization. And this is just, this is an example of what you get here. So blue, that's an increase of information going to that area under high synchronization. And the red means that there's an increase of information going from that area under high synchronization. So in this case, this would suggest that it's the parietal areas up here that's driving this alpha network. Yeah, so for example, if you just compare it with the undirected graphs, you have like all of these areas that don't show an alpha synchronization. You have a decrease of information going there as well. But then interestingly, you have, for example, these areas here that show quite a lot of synchronization, which there's no increase of information going from these areas. For instance, like parietal areas could be driving this. Yeah, so this is still very new. So we just started working on this. So I definitely think it adds a lot of extra explanatory things. So with that said, to summarize then, these macroscopic oscillations that we see in MEG, they thought to arise through the coupling of local populations, either directly or indirectly. And the global patterns of macroscopic oscillations, they vary under different brain states and from individual to individual. And then to just touch finally that, of course, a future challenge here is still to understand the mechanistic consequences of macroscopic oscillations. Like how is it, for example, impacting high frequency oscillations where we get a lot of, where a lot of the information about what's going on is kept. So, yeah. With that said, thank you very much.
You any questions?
Full episode during memory maintenance, but maybe some of these oscillations, specifically the macroscopic, but a little higher ones, they might happen in bursts. So maybe it would be more meaningful to calculate it during the specific burst, because you might have a very strong coupling during the burst, but almost no coupling at all. So on average, you would get the same phase coupling value as to another oscillation or whatever who is just weak in general, but a little bit on.
Yeah, so I didn't show that now. We have, because you mean like during this 1 second, there might not be a coupling during the whole 1
exactly.
second.
It makes no sense to calculate the phase locking value when the oscillation is not there.
Yeah. What we see when we calculate, like, when we look at the rolling average over the whole trial, I don't have that picture here, but what you see is that you get an increase during the maintenance period, and then it decreases as the item is shown, and then it increases again. And then it's quite, for most of the, it was almost present throughout the whole delay period. There was one subject though that had, just as you said, and I don't know why, but it was super consistent over time. Then this task, they got like a burst of the alpha just in the first 500 milliseconds, and then it was nothing. And they didn't get it for this one, but for that one. And it was the same like throughout every measurement session. So that one was more bursty, but in general, it's present during the whole delay period.
So on single trial basis.
On single trial, well, it's you get very noisy estimates when you do it on the, because we just have 1 second anyways. So just see, of course, but now I mean that would still take an average over the whole over all the trials. But I have done it within like single trials as well, but yeah, I mean from the equation, like it's not really, it's not really great just to do within 1 second.
So how different were these 4 participants in terms of capacity?
We had a little problem towards the end because they all reached the same point in the end. So in the beginning there was quite a big difference.
Yeah, I was thinking of your question. Maybe then in the beginning you could look at if that averaged correlates with the performance or not.
Yeah. The problem there is again that like, we can look within single trials and see if they completed, if they did correctly or not. I haven't done that because the PLV values that I get from within just that second, they're not great. They're very noisy. So, but I haven't actually tried to see if I can find any just correlation on trial to trial. If that was.
Of course, your scale of one little burst has to be reconciled with the duration of the working memory task as a whole, which is, I don't know, seconds long or something.
Yeah. So, but basically we're dividing the trial up into multiple conditions, right? Depending on the load. So there is 1 second condition. So the whole trial is like. And then if you also, what's difficult there is that like if you want to correlate, because if you, for example, if you're expecting that like one person, if 2 people have, if one person has a working memory capacity of 4, another one has 6, and maybe what's happening in the end, that's predictable on the performance, mostly, I guess. So that means they only have this 1 second as well to work with their.
Yeah.
So it's because that's the maintenance that they then actually use to answer. So, yeah, it's a bit tricky.
On that comment too, because I also had this experience of when computing this for the nonlinear oscillators, the ones I was commenting before in my talk, they have the same problem. They burst and then they stay still for a long time. So even if they are not synchronous at all, just because they stay in the same state for a long time, these kind of values will be very high. So it turns out that it is possible always when you do this kind of stuff, if you do Hilbert transform or something like that to extract phases from the time series, you can linearize these phases because at the end it's a problem of densities, that you have a huge density of signal in one place of the phase and not a lot in the other one. So there is always a possibility to just do a change of variables so the density is uniformly distributed, and then you compute these Kuramoto phase locking values, and then they improve considerably because you remove this problem of having everybody stacked at the same place of the phase space.
All right, so that's what you showed in the.
They get the stack for a lot of time, and then you just have some bursts. So if you try to get, are these oscillators synchronous? The answer, if you just take the phases and put it into this kind of like PLB, for example, the answer is always yes, because even if the bursts are completely at different times, most of the phase it's always at the same place, but you are not interested in that. You want to see correlations between them. So these kind of tricks are necessary at some point if you want to disentangle this.
All right, any more questions? Okay, thank you once again. We have a break until 3 o'clock.
Yeah.